The next topic is PM junction, a single piece of pure semiconductor with one half doped with trivalent impurity to obtain the p-type and the other half doped with pentavalent impurity to obtain n-type is called as PM junction. I'll repeat again. A single piece of pure semiconductor with one half doped with trivalent impurity to obtain the p-type and other half doped with pentavalent impurity to obtain n-type is called as PM junction. Next, I'll explain the formation of PM junction. So, the holes are majority charge carriers in p-type and free electrons are majority charge carriers in n-type. I hope you know this now. I'll repeat again. The holes are majority charge carriers in p-type and free electrons are majority charge carriers in n-type. The holes carry positive charge and the electrons carry negative charge. Some holes diffuse from p-type to n-type through the junction. Some holes diffuse from p-type to n-type, p-type to n-type through the junction, and some free electrons diffuse from n-type to p-type, from n-type to p-type. Okay, so after this, a layer of positive and negative immobile charges is formed across the junction like this. Positive and negative charges are formed here. Okay, so as a result, the potential difference is set up across the junction called potential barrier. So this is the potential barrier here. Okay, so this is the potential barrier. This stops the further diffusion of immobile charges. The free electrons and holes are absent around the junction. The region around the junction free from mobile charge carriers is called depletion region or depletion layer. So this is the depletion region here. Okay, so this part is called as depletion region. The thickness of depletion region is about 1 micron or 10 to the power of minus 6 meter. So it is very small, 1 micron or 10 to the power of minus 6 meter. The thickness depends on the concentration of doping. I'll repeat again. The thickness of this depletion region depends on the concentration of doping. The thickness of the depletion region decreases with the increase in the impurity concentration. The thickness of the depletion region decreases with increase in impurity concentration. The junction potential difference increases with increase in impurity concentration. The junction potential difference increases with increase in impurity concentration. These are few important terms that are present in this chapter. The first one is potential barrier or junction potential difference. The potential difference across the junction which prevents the further diffusion of holes or free electrons is called as potential barrier. I'll repeat again. The potential difference across the junction which prevents the further diffusion of holes and free electrons is called as potential barrier. The next one is depletion region. The region around the junction free from mobile charge carriers is called as depletion region. I'll repeat again. The region around the junction free from mobile charge carrier is called as depletion region. The next one is diffusion current. The current due to concentration difference in the majority charge carrier when PM junction is formed is called as diffusion current. I'll repeat again. The current due to concentration difference in the majority charge carriers when PM junction is formed is called as diffusion current. The next term is drift current. The current due to minority charge carriers when electric field is set up by the immobile ions in the depletion region is called as drift current. I'll repeat again. The current due to minority charge carriers when electric field is set up by the immobile ions in the depletion region is called as drift current. The next one is drift. The motion of carriers due to the electric field. The motion of charge carriers. The motion of charge. The motion of charge carriers due to the electric field is called as drift. The motion of charge carriers due to the electric field is called as drift. The PN junction is commonly called as semiconductor diode. For silicon diode, the junction potential difference is around 0.7 volts. For germanium diode, it is around 0.38 volts at room temperature. The symbol of semiconductor diode is this one. So this is PM. So this is the semiconductor diode. This is the symbol of semiconductor diode. The arrow points the P side to N side. The arrow indicates the direction of conventional current. The next topic is biasing. When no external potential difference is applied across the PN junction, it is said to be unbiased. I'll repeat again. When no external potential difference is applied across the PN junction, it is said to be unbiased. But when the PN junction is connected to an external potential difference, it is said to be biased. I will repeat again. When the PN junction is connected to an external potential difference, it is said to be biased. So this biasing can be classified into two types. One is forward bias and the other one is reverse bias. So in forward bias, first one is forward bias. A PN junction is said to be forward bias if P type is connected to the positive terminal and N type is connected to the negative terminal of the battery. So this is the circuit here. The P type is connected to the positive terminal and N type is connected to the negative terminal. So this is positive and this is negative. So this is forward biased. In forward bias, P side is connected to the positive terminal and N type of the battery and the N type is connected to the negative terminal. I hope you know this now. So the direction of applied voltage is opposite to the built-in potential. So V, the direction of the applied voltage, that is V, this is the applied voltage. It is opposite to the built-in potential V0. So V0 is the built-in potential. So as a result, the depletion layer width decreases and the barrier height is reduced. So the depletion layer width decreases and the barrier height is reduced here, as you can see in the barrier potential as from this figure. So here the width was, without battery it was from here to here, but with battery voltage the width decreased from here to here. Now the length is only this much. Okay, so the effective barrier height under bias is V0 minus V. So the effective barrier height under bias is V0 minus V. Now the junction resistance becomes almost negligible and thus diode permits the current to flow through it. I'll repeat again. The junction resistance becomes almost negligible. The junction resistance that is present here becomes almost negligible and the diode permits the current to flow through it. The next topic is working of a diode in forward bias characteristic. Working of diode in forward bias characteristic. So this is the circuit here. So this is the voltmeter, this is the diode, and this is milliammeter, this is switch, and this is battery. So all these are connected in this form. So I hope you all know that in forward bias, positive terminal of the battery is connected to the P type and negative terminal of the battery is connected to the N type. During forward bias, the applied voltage opposes the junction voltage. That is, applied voltage cancels the potential barrier. The junction resistance decreases here. I will repeat again. The applied voltage cancels the potential barrier. The junction resistance decreases. The majority charge carriers, holes and free electrons can cross the junction easily. I'll repeat again. The majority charge carriers, holes and free electrons can cross the junction very easily. The current flows through the junction. The current will flow through the junction. This current is called as forward current. I'll repeat again. The current that flows through the junction is called as forward current. The forward current increases with increase in applied voltage. I'll repeat again. The forward current increases with increase in applied voltage. The applied voltage at which the forward current increases rapidly is called as knee voltage, which is represented by VK. This is knee voltage. I will repeat again. The applied voltage at which the forward current increases rapidly is called as knee voltage. After knee voltage, the forward bias characteristic is almost linear. I will repeat again. After knee voltage, the forward bias characteristic is almost linear. The forward bias resistance is very low. For ideal diode, the forward bias resistance is almost zero. During forward bias, the diode conducts the current to flow through it. I'll repeat again. During forward bias, the diode conducts the current to flow through it. The graph of forward current versus forward voltage is called forward bias characteristic. That is here. So the current and voltage, the graph which comes like this. So the next topic is cut-in voltage. This is also called as threshold voltage or knee voltage. So it has three names. One is cut-in voltage, the threshold voltage and knee voltage. So all are same. The minimum forward voltage in which the diode goes to on state with increase in current is called as cut-in voltage. I'll repeat again. The minimum forward voltage in which the diode goes to on state with increase in current is called as cut-in voltage. For germanium, it is around 0.2 to 0.3 volts, and for silicon, it is around 0.6 to 0.7 volts. The next topic is reverse bias. A PN junction is said to be reverse biased if P type is connected to negative terminal and N type is connected to positive terminal of the battery. That is called as reverse bias. I'll repeat again. A PN junction is said to be reverse bias if P type is connected to negative terminal and N type is connected to positive terminal of the battery. Is called as reverse bias. So this is how the reverse bias works here. So this is the circuit diagram. So in reverse bias, N side is connected to positive terminal and P side is connected to negative terminal of the battery. I hope you know this now by now. The direction of the applied voltage is same as the direction of the barrier potential. I'll repeat again. The direction of the applied voltage is same as the direction of the barrier potential. As a result, the barrier height increases and the depletion region widens. So here you can see that the depletion region has widened a bit. Okay, so it will get widened a bit. Okay, a high resistance path is established here. The effective barrier height under reverse bias is V0 plus V. V0 plus V as shown in the figure. As you can see here, from this figure, it is said to be V0 plus V here. This suppresses the flow of electrons from N to P and holes from P to N. I will repeat again. This suppresses the flow of electrons from N to P. From N to P and holes from P to N. Okay, so the diffusion current decreases enormously compared to the diode under forward bias. I will repeat again. The diffusion current decreases enormously compared to the diode under forward bias. The current under reverse bias is essentially voltage dependent up to a critical reverse bias voltage known as a breakdown voltage. I will repeat again. The current under reverse bias is essentially voltage independent up to a critical reverse bias voltage known as breakdown voltage. Known as breakdown voltage. This is said to be VBR. So this is breakdown voltage. This breakdown voltage, when it becomes equal to the applied voltage, that is VBR is equal to V. So here at this case, the diode current increases sharply as in order of microamperes. I will repeat again. The diode current increases sharply in order of microamperes when this VBR is equal to V here. This is the working of reverse bias characteristic. This is the circuit. So here we have voltmeter, we have PM Junction Semiconductor Diode. This is microammeter, and this is a battery, and this is a switch here. All these are connected in this form. So in reverse bias, positive terminal of the battery is connected to N type and negative terminal is connected to P type. As I hope you can clearly see that in this circuit here. So in reverse bias, positive terminal of the battery is connected to N type and negative terminal of the battery is connected to P type. So that is obviously done here. So during reverse bias, the applied voltage adds to the junction voltage. The majority charge carriers are holes and free electrons cannot cross the junction here. I will repeat again. During reverse bias, applied voltage adds to the junction voltage. The majority charge carriers, holes and free electrons cannot cross the junction. However, a small current flows through the junction due to minority charge carriers. This current is called reverse current or leakage current. At a particular applied voltage, the reverse current suddenly becomes maximum. This reverse voltage is called breakdown voltage, that is VB. The reverse resistance is very high here. The reverse resistance is very high. For an ideal diode, the reverse bias resistance is infinity, that is R R is equal to, this is reverse bias resistance, which is almost equal to infinity here. The diode does not conduct due to reverse bias. The graph of reverse current versus reverse voltage is called as reverse bias characteristic, as you can clearly see the graph here. So this is reverse bias characteristic. So the next topic is reverse saturation current. The reverse current, which remains constant with increase in reverse bias voltage, is called as reverse saturation current. I'll repeat again. The reverse current, which remains constant with increase in reverse bias voltage, is called as reverse saturation current. It is in order of 10 to the power of minus 6 ampere. Next one is breakdown voltage. The reverse bias voltage at which the reverse current increases sharply. The reverse bias voltage at which the reverse current increases sharply is called as breakdown voltage. The next one is dynamic resistance. It is the ratio of small change in voltage delta V to a small change in current delta I. So I'll repeat again. It is the ratio of small change in voltage delta V to a small change in current delta I. So it is given by the expression RD is equal to delta V divided by delta I.